Hello guys, let's derive this standard limit form and let's do it without L'Hospital's rule because this is in the form 0 by 0 and it would be right but it would be too boring because here just do the derivative of the top which will be n x to the power n minus 1 and here this a is constant so its derivative will be 0 and on the bottom you'll have 1 minus 0 and you'll have n x to the power n minus 1 and in place of x put a and you'll get this video over. But let's not do that. Let's do synthesis, or I meant to say synthetic division. I don't want to make it too obvious for you guys. So I've done some proofs in the past that x minus a is a factor of this over here. Now let's do synthetic division. Now we see in the denominator we have x minus a. So what I'm going to do is write x minus a equals to 0 and I have x equals to a. We're not going to put it here. We're doing synthetic division. Let's not forget that. So I'm going to put this a over here. Now what I'm going to write is the powers of x in decreasing from x to the power n all the way to the constant term. So here from x to the power n, the next one will be x to the power n minus 1. The next one will be x to the power n minus 2. And the next one will be x to the power n minus 3 and so on until you get the constant term. Now before that, let's write the previous power of x before the constant, which will just simply be x to the power 1. I'll write it over here, x to the power 1. Now below it I'm going to write its coefficients. So for x to the power n, I'll have just one of them. This is what we're focusing on. And we don't have any of these middle terms, so all of their coefficients will be 0, 0, 0, 0, 0, and the constant is minus a to the power n. Now let's do synthetic division. We'll put this down and bring it over here, and I'll just make this over here. Now this a will multiply with that, it will give a. These two will now add them, we'll get a. Multiply, we'll get a square, add them, we'll get a square. Now this pattern will continue. It will be a cube for x to the power n minus 3 and a cube here, a to the power 4, a to the power 4 and so on. Now what about for x to the power 1? What will that be? Well, we have to find some kind of pattern. Let's look at the power of x. So we have x to the power n, let's write it as x to the power n minus 0. So this one we can write it as a to the power 0. So when we have n minus 0, we'll have a to the power 0. N minus 1, a to the power 1. N minus 2, we'll have a to the power 2. N minus 3, a to the power 3. So for x to the power 1, well, I can write it as x to the power n minus n minus 1. So that means I'll have a to the power this part, which is n minus 1, and this constant term. Well, I can write it as x to the power n minus n. So that means, or simply we can just multiply. So we know we'll have this over here. A multiplied with this, we'll just have a to the power n. And oh, I was almost about to do a wrong thing. I was about to write a to the power n over here. That won't happen. But here, as you can see, we have a to the power n plus minus a to the power n, which will result in 0. So this 0 part is our remainder, which I'll denote it as r. And for this limit, as you can see, I'll rub it over here. This will be the same as this part over here. So to find out what this part is, what the quotient is, we'll just have to multiply this with the decreasing power of x. So the quotient will start from the power 1 below from what it started. So it will start from x to the power n minus 1 and it will multiply with this, the coefficient. So it will be 1 times this plus a times, in the decreasing form it will be x to the power n minus 2 plus a square x to the power n minus 3 and so on until here the last term will just be a constant, and that will simply be a to the power n minus 1. Now we know this is the same as, well, I'll write it over here, x tends to a or x approaches a, x to the power n minus 1 plus, oh, actually I'll write it over here. We'll have this, and now we can put the limit in. So we're going to have a to the power n minus 1 plus a into a to the power n minus 2 plus a square into a to the power n minus 3 plus, and so on till the end. I'll just write add a to the power n minus 1. Now, due to the indices law, this will be a to the power 1 and this will add. So we'll have a to the power n minus 2 plus 1, a to the power n minus 3 plus 2, and the next a to the power n minus 4 plus 3. So in all of these terms, what we'll eventually have is just a to the power n minus 1, like this. Now, we're almost at the end. We just need to figure out one thing. How many a to the power n minus 1 terms are there? Well, let's find some pattern. Let's go over here. So as you can see, we have in the coefficients a to some power. Well, not any power, they're in the increasing form. So we can find out which term is the last term and determine how many terms there are altogether. So for this one, I'm going to write it as a to the power 0, because that's the same thing as 1, and this is just 1 multiplied by that, and I'll make it a bit nicer. Now let's find the pattern. For the first term, we'll have a to the power 0. For the second term, we'll have a to the power 1. Third term, a to the power 2. Fourth term, a to the power 3, and so on, and we have ending in n minus 1. So when the power is n minus 1, to get the term, which is it, well, we just add 1. So that means this is the n minus 1 plus 1th term, meaning this is the nth term over here. That simply means altogether there are n terms, and that means we'll have n times many of this. So we'll just have n times e to the power n minus 1. Now that is the proof using synthetic division. Well, not proof, we actually derived it. So if you guys know something new, please like and subscribe. Thank you.